Okay, good morning, everyone. So today we start our presentation on equilibrium and refinement. This is the outline of the presentation. I'll talk about briefly about Nash Maximal subsets, about what we call a set of pure best replies. I'll start with the first refinement, isolated and regular equilibrium. I'll talk also about quasi-strong equilibrium, perfect equilibrium, proper equilibrium, and finally, with communication and correlated equilibrium. So first of all, as we said in class, for biometrics games, the set NE of all equilibrium points is the union of a finite number of what we call polytopes. We call also maximal Nash subsets. So the set of vertices of the maximal Nash subsets defines what we call the set of extreme Nash equilibrium. And each Nash equilibrium can be obtained by convex combination of some other extreme Nash equilibrium. So the set NE of all equilibrium points is in fact the union of a finite number of maximal Nash subsets. What is a maximal Nash subset? A subset T, which is in NE, is called a Nash subset if and only if every pair of elements in T is interchangeable. Yani if you take two equilibria, you have with components, for example, for a dynamics game, the first equilibrium x1, x2 belongs to T, and the next equilibrium y1, y2 belongs to T, then this pair is interchangeable. Yani x1, which means x1, y2 is also in T, and y1, x2 is also in T. Okay, so a Nash subset T is called maximal if it's only properly contained in itself. So it's not contained in any other Nash subset. So any extreme equilibrium is in fact an extreme point of what we call these maximal Nash subsets. And one of the things we could do is that we could enumerate all maximal Nash subsets corresponding to a biometrics game. And we can use this using what we call an algorithm for the enumeration of maximal cliques in a graph theory. So for example, if you define G as the graph obtained by the vertices and the arcs linking the maximal Nash sets or the equilibria. So this is the graph obtained from the analysis of extreme Nash equilibria in E. So the extreme points of NE define what we call the set of nodes, yani the extreme, which means that the extreme points here are the extreme Nash equilibria. And we will put an edge between every pair of extreme Nash equilibria if they are interchangeable. And a maximal clique is a graph with a maximum connectivity. So you could enumerate all the maximal Nash subsets. So for instance, in this example, where we have 3 rows and 4 columns, we have here for this game, which is 3 by 4, taken from Born et al., we have this set of 10 extreme Nash equilibria. And you can see right away that the first 6 extreme equilibria, they share the same vector x1, the same vector for of probabilities for or vector of strategic play by player 1. So the first maximal Nash subset T1 contains these 6 extreme Nash equilibria, and of course the components of this maximal Nash subset are 2 by 2 interchangeable. Next, you can see that equilibria 4-8 are also interchangeable because they have the same x2. Also 6 and 10, they are interchangeable because they have the same x2. 7 and 9, they have the same x1. And 7 and 10, they have the same 7 and 9, they have the same x2. 7 and 9, they have the same x1. And finally, 8 and 9, they have the same x1. So these are the 6 maximal Nash subsets for our biometrics game. Okay. Now we move on to the second subsection or the second section in this presentation. We talk what we call a pure best replies set. So for an equilibrium x1, x2 of a biometrics game, we define MA x2, which belongs here. This is the set of pure best replies for player 1, because x2 here is a variable. It is defined as the set of pure best replies of player 1 against x2. So MAX2 contains, in fact, the indices of the strategies belonging to player 1, strategies in N, that do provide a best response to when x2 is played. So it's, in fact, formally all the i's in N such that AIX2, which means row I of A multiplied by X2 is a maximize this function, AKX2. Okay. Similarly, for player 2, you're going to have the set of pure best replies of player 2 to X1 by B. So it gathers all the J indices such that X1 TBJ is maximized. So once we have this formal definition of sets of pure best replies, we can now talk about what we call also the carrier of X1 and X2. What is the carrier of X1 is the set of all indices of strategies that are given a non-zero probability when the player is playing. So CX1 is the carrier of X1, CX2 is the carrier of X2. And this way we have two definitions, one for the pure best replies set, and one for the carriers. And we'll see when these two sets are respectively equal, we will have what we call quasi-strong equilibrium. So quasi-strong equilibrium is an equilibrium profile such that C of X1, so the carrier of X1, is the set of pure best replies of player 1, and the carrier of X2 is the set of pure best replies. In other ways, what does it mean? It's quasi-strong, which means that the player randomized on all his strategies that form a best reply to X2. An equilibrium profile X1, X2 of a matrix game is isolated. That's the second thing, isolated. If there exists a neighborhood of X1, X2, such that this is the only equilibrium in its neighborhood. So another refinement is about isolated. And another way to see things is that an isolated equilibrium will end up to be an extreme Nash equilibrium that defines by itself a maximal Nash subset. So it's an isolated Nash, extreme Nash equilibrium. So what we have is that if you have an isolated and quasi-strong equilibrium, we have what we call a regular equilibrium. So one of the definitions, that's what we see here. That's what is shown by Jensen in 1987. 1987, Jensen showed that an equilibrium of a matrix game is regular if and only if it is isolated and quasi-strong. Another way that to prove that we have an isolated equilibrium, we've talked about this in class, is that if you take the quasi-strong equilibrium you obtain it has to be quasi-strong. So C of X1 is equal to MAX2, and C of X2 is equal to MX1, M of X1B. And you have a bimatrix game where the matrices, the payoff matrices are non-negative. Then X1, X2 is said to be isolated if the cardinality of CX1 is equal to the cardinality of CX2. First of all, which means here that these two submatrices you're going to extract from A and B, the submatrix A, I, and G, where I belongs to CX1 and J belongs to CX2, and the submatrix you're going to extract here from B, Bij, these are two square matrices because of the cardinality equality here. They need to be non-singular, which means inverted. If you have such a condition, then you have an isolated equilibrium. So basically, you don't need to go through the enumeration of all maximal Nash subsets to prove that you have an isolated equilibrium. Okay, so what Jensen did, he showed that a quasi-strong and isolated equilibrium is stable against slight perturbation of the payoffs of the game, and this defines what we call regular equilibrium. And in fact, regular equilibria have all kinds of robustness properties. Small example. So let A and B be the payoff matrices of a game, and if you use our X game software, you see that this game has three extreme Nash equilibria. One of them, which is 0, 1, 1, 0, which means player 1 plays 0, 1, player 2 plays 1, 0, is quasi-strong and isolated. This extreme Nash equilibrium, quasi-strong and isolated. It's easy to show. I invite you to do it. And the two remaining two extreme equilibria, which are 1, 0, 0, 1, and 1, 0, half, half, they do define a maximal Nash subset because you see that share the same X1. And they both are non-isolated and non-quasi-strong. So you can see that one of the conditions of quasi-strong equilibrium fell down. So now we talk about what we call perfect equilibrium. So a Nash equilibrium, first of all. So let's assume you have in hand or at hand X1, X2, which is a Nash equilibrium of a matrix game. And if there is a unit vector x1 such that x1a is greater or equal than x hat 1a, such that x1a is not equal to x1 hat a, يعني, which means in other words that x1a dominates x1 hat a. Or if there is a unit vector x2 such that bx2 would dominate bx2 hat, then that equilibrium x1 hat, x2 hat is not perfect. Otherwise, the equilibrium is said to be perfect. So in other words, if a perfect equilibrium is what we call an undominated. So it's formed by the two pairs of x1 and x2 that are not dominated. So what Selton did in 1975, he was able to introduce the perfect refinement of a Nash equilibrium concept. And the perfect refinement defines what we call stability conditions with respect to slight imperfections of rationality, sometimes called trembling hand perfection. In other words, every player is picking a non-dominated vector of mixed strategies. Okay. For instance, for this game, which is 3x4, which already talked about, we have 10 extreme Nash equilibrium. The second extreme Nash equilibrium, which is 0, 1, 0, 0, 1, 0, 0, is not perfect. In fact, you could see that it's dominated by 0, 1, 0, 0 for x2 hat. So we can see that x2 hat, which is 0, 1, 0, 0, is dominated by 0, 0, 1. Okay, and 8 of the 10 remaining extreme Nash equilibria, of the whole 10 extreme Nash equilibria, are found to be perfect. Among these are 1, 3, 4, 6, 7, 8, 9, and 10. And what Selton was able to show is that every biometrics game possesses at least one perfect equilibrium. Okay, so the last part here we'll talk about we call epsilon proper equilibrium. What is an epsilon proper equilibrium? First of all, an epsilon proper equilibrium is said to be defined for some epsilon which is very small, marginal, and strictly positive if the following conditions are satisfied. So let's see what are the conditions. If we have two strategies I and H, which belong to a set of strategies N of player 1, then AIX2, if AIX2 is less than AHX2, which means that the payoff that is provided by strategy I is always less than the payoff provided by strategy H. Then what could you do is that the probability you would assign to strategy I should always be dominated by epsilon times the probability assigned to X. To H by player 1. Okay, which means in other words that if H is dominating I anyways for X2, then you shouldn't assign more than epsilon times X1H probability to X1I. Same thing for player 2. X1BJ is less than X1BL for two strategies J and L belonging to the set of strategies of player 2. Then if you have X1BL, which means strategy L is always a better response than strategy BJ, then you will always have to assign a lower probability to strategy J, less or equal to epsilon times X2A. Okay, and one other condition to make this equilibrium epsilon proper is that all the strategies, in fact, all the X1Is, X2Js should be played with a non-zero probabilities. And the main idea is that the proper refinement of a Nash equilibrium is that the reasonable player would try harder to avoid important mistake, because here I and J are important mistakes with respect to H and L, then he or she would try to avoid small ones. Okay? So while any proper equilibrium profile is shown to be perfect, we can easily show that any equilibrium profile satisfies these conditions is perfect, but perfect equilibria are not always proper. And Meyerson, 1978, defines what we call proper equilibrium to be the limit of an infinite sequence of epsilon proper equilibria, which means, in other words, that this epsilon proper equilibrium, when epsilon goes to 0, should converge to our proper equilibrium. Okay, so which with E converging to 0. So an equilibrium x1 hat, x2 hat is said to be proper if there is a sequence of epsilon k proper equilibria such that the limit when k goes to infinity of epsilon k goes to 0, and the epsilon proper equilibria sequence x1k, x2k should go to x1 hat, x2 hat when k goes to infinity. And Meyerson showed that every biometrics game possesses at least one proper equilibrium. Okay, so in this case in class we've taken this example. Here in this case we have a 5 by 5 parameters game, and we can easily get 7 extreme Nash equilibrium for this game. And all of them are perfect, except the second extreme Nash equilibrium. And for 4 extreme perfect, 3, 5, 6, 7 are also proper. And one of the things we were able to show is that this sequence, which is in fact provided from equilibrium 3, which is 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. This sequence converges to equilibrium 3 when epsilon goes to 0. And to be able to define this relationship, what we did is that, first of all, for x1, we've taken the vector 0, 0, 1, 0, 0. We multiplied it by a, and we found out that, well, we will have the third column, which is 5, 0, 6, 5, 6, okay, that potentially could be played, which means that there are other relations between strategies 3, 5, and 4, and 1, okay? And here we have we made a huge preference for player 1 to play strategy 3, because we want our equilibrium to converge to this 0, 0, 1, 0, 0. So strategy 3 is given the highest probability, and then also strategy 5. Okay, then comes strategies 1 and 4, and finally strategy 2. And we did the same for the strategy of the second, for the vector of mixed strategies for player 2. Okay. So I'll stop here. The rest of material we've seen in class is not subject to evaluation, so we won't have any question on correlated. Thank you very much, guys, and see you soon.